Welcome to the ninth session on fundamentals of computers. I'm Manibhushan D'Souza, and today we are going to look at basic theorems and properties of Boolean algebra. So this will be the topic for today's session. We will look at some of the basic theorems and the properties of Boolean algebra. Now, one of the principles that is used in Boolean algebra is the principle of duality. The duality principle states that every algebraic expression deducible from the postulate of Boolean algebra remains valid if the operators and the identity elements are interchanged. What is the meaning of that is, if you deduce any algebraic theorem based on the postulate of Boolean algebra, then the dual can be obtained by changing the identity as well as the operator. To put it in other words, this principle implies that if the theorem is proved based on the postulate of Boolean algebra, then the dual theorem can be obtained by interchanging the OR operator with the AND operator and the 0 with the 1. So we get the dual automatically, and there is no need to prove this particular thing. Let's look at the example. Now, by the way, just to recall, what is a postulate? Postulates are the basic assumption that are assumed to be proved and or that are assumed to be valid, and there is no need for a proof for this one. However, the theorems that are derived from the postulate has to be proved. So you have to algebraically prove that such a theorem is valid. Now let's look at the postulates. One of the postulates that we are all familiar with the Boolean algebra is the postulate that includes the identity element. So this is the one that introduces the identity element in the Boolean algebra, and this postulate is, if x plus 0 is equal to x, then we know very well that 0 is the identity element. What is the dual of this? Replace the plus with the dot and 0 with 1. So what you get is x dot 1 is equal to x. So that's the idea that we are going to use it. Now let's look at the other postulate. The other postulate is x plus x bar is equal to 1. Now how do I get the dual out of it? To get the dual out of it, you replace it with the plus with the dot and 1 with 0. So what you get is x plus x dot is equal to 0. The next dual out of this one, next theorem that we are going to prove it later, is x plus x is equal to x. What is the dual of it? If you notice over here, in the previous case we had 1 and zeros, whereas here we don't have 1 and 0, so we just put the dot over here. So x dot x is equal to x, and that is the dual. If you look at the next one, x plus 1 is equal to x. In this case we are replacing the plus with the dot and 1 with 0. So we will replace 1 with 0 everywhere. So what you get? X dot 0 is equal to 0. Now this is complement. The complement of complement is equal to itself. So x bar is the x complement. X complement of x complement is x itself. Now let's look at the next postulate. So these three are the theorems that are there in the Boolean algebra, and this particular theorem is called as involution. Okay. So let's look at the next postulate, and the next postulate is the commutative. So x plus y is same as y plus x. What is the dual of it? Replace plus with the dot. So what you get? X plus x dot y is equal to y dot x. Let's look at the associative here. So x plus inside the parenthesis y plus z is equal to x plus y inside the parenthesis plus z. Now how do we get the dual out of it? To replace every plus with the dot, and there is no 1 and 0, so there is no need to replace them. So what you get is x into y dot z is equal to x dot y dot z. Let's look at the next distributive postulate. Now this is the postulate here. So distributive postulate says that x inside bracket y plus z is equal to x dot y plus y dot z. How to get the dual out of it? Put the dot here. So put the dot here. Okay. And replace put the plus here, not the dot, sorry. Put the plus here and replace the dot here. So what you get? X plus, you have put the plus here, x plus y dot z. So that's what you get. What about the other side? Other side is put the plus in between, dot here, plus in between. So what you get? X plus y dot, so this dot, and y plus z. Now let's look at one other theorem, and the other theorem is De Morgan's theorem. So in the De Morgan's, what you get is x plus y inversion is equal to x inversion y inversion, or what is the dual out of it? You put the dot here and you put the plus in between. So x dot y bar is equal to bar, or inversion is equal to x inversion plus y inversion. The next one is the one more theorem. These two are the theorem again. So x plus y, x plus xy is equal to x. What is the dual out of it? You put the dot here, you put the plus in between. So x in the inside bracket, x plus y is equal to x. These are the theorems, and let's try to prove the theorem. So we will start with the theorems, and then we will prove them using the, and we will also try to prove the duality of these theorems. So let's start with the first theorem, and the first theorem says that x plus x is equal to x. How do you prove that thing? So x plus x, now if you take the second postulate, now the second postulate is, if you look at here, postulate 2 is, if you multiply it with 1, you get the x itself. So there is no change in the thing. So what you are going to get is, this is one term here, you multiply it with the 1, you get back the same term. So that's what the postulate 2b says. However, now let's look at this 1 here. How can I get this 1? Let's go to the postulate number 5 here. So what does that postulate 5 says? So x plus x bar is equal to 1. So let's look at that. So let's go back here, and I'm going to replace this 1 with the x plus x bar. Okay, now let's look at the postulate number 4 here. So what does that postulate number 4 says? Now the postulate 4 is a simplest one, and what does it says? Now if you have x plus y dot y plus z, then you can combine y and z together and keep the x separate. So let's look at that one here. So you have, look at here, you have x here. So this could be y, this could be z. Okay, so we have y and z. Okay, and we have the x common here. So we can take out this x here and we can combine y and z. So if you take this x common here in this case, so this is, you take it as y, this you take it as z. You take x common here because you take this x common and take this y, this you took it as y, you take this y and you took this as z, so you take this z, so what you get is x plus x bar. Now let's look at the one over here. So there are two postulates here, x plus 1, x dot 1 is equal to x. So let's go here. So where is this? Not this one. This postulate, second postulate, x plus x dot, these are all plus, thanks to Microsoft PowerPoint for automatically changing this. This is not a semicolon actually, this is that dash. Okay. PowerPoint, somehow when you try to save the PowerPoint, it simply changes that a dash with the apostrophe. So sometime automatic helping could be too dangerous, but assume that that is the dash there, not the inverted comma there. So that's why I'm not bit comfortable with that. Okay, just realize that it has changed everything, but anyhow you can get know that this is the inversion dash here, not the one that we are using. Not, this is not the one, it is just the dash. Okay, so let me come back to this one, x dot x bar. So this is what you have, x plus x dot is equal to 0. So that is what you're going to replace it. So this part you're going to replace it with the 0. Now x plus 0, you know this postulate, the postulate number 5, that says x plus 0 is equal to x, that not the 5, the 2 says that x plus 0 is equal to x, and that is what you get. So you started from here and finally you reached up to this point. Okay, let's look at the dual out of it. The dual theorem says it's one and the same. So what is that we are doing? So you have x dot x is equal to x. So you take x dot x, add plus to add 0 to it. Now if you look at this postulate here, if you add 0 to x, you get x itself. So that is what is been done over here. So if you consider this whole thing as x, so this whole thing is x, if you add 0 to it, it's not going to make any difference. However, what is this 0? So 0 can be written as x dot x bar. So how did you get that thing? You know very well. X dot x bar is equal to 0. So this is what I am replacing it, x dot x bar. So I am replacing it with that. So you replace 0 with that. Now take the fourth theorem, and the fourth theorem is an interesting one. And what does the fourth theorem says? Now you can take the fourth theorem, or if you are in biology, if you are from the algebra, you can always take the x from this thing and then do it. Okay, so that is also possible, but let's go with the fourth theorem. Now what does that fourth theorem says? I mean, fourth postulate says. Now when you look at this postulate number over here, so x plus y and x plus z is equal to x plus yz. And that is what you are doing here. So you have x dot y and x dot, not this one, the other one, the dual out of it. So the dual also is the same thing. So what does the dual say? If you have xy and xz, take x common and put y plus z. So this is what you're going to do it now. So you are going to take the x common, and then you're going to put x plus x bar over here. Now what is x plus x bar? We know very well. X plus x bar happens to be 1. So you just replace it with 1. And what is 1? X dot 1, and we know very well x dot 1 is x itself, okay, from the postulate number 2b. So if you look at here, x dot equal to x. So you started with x plus x dot x is equal to x. Now let's look at one more postulate. X plus 1 is equal to 1. So how do you prove that? X plus 1, and we know very well, if you multiply it with the 1, x dot 1 is equal to x itself. So you take x plus 1 dot x plus 1. So this is x dot 1. It's a commutative law, so you can always do that thing. And what is 1, by the way? So 1 is nothing but x plus x bar. So you replace this one with x plus x bar. Now we know the theorem, that is 4b. If you look at 4b over here, what does it say? X plus y plus x plus z is equal to, take x common, y z separately, and that's what you are going to do it. X plus y, x plus z, x, take x common and put the y and z together. Okay, what is x dot x bar dot 1? Okay, so we know that if you take any x, anything dot 1 is equal to x itself. So we can say anything dot x is equal to x itself. So in this case it is x bar dot 1 is equal to x bar. What is x plus x bar? If you look at this, x plus x bar according to the postulate number 5 is 1. So you replace it with the 1. So what you get here is x plus 1 is equal to 1. Now what's the dual out of it? Dual is simple. You replace it, the plus with the dot, 1 with the 0, 1 with the 0. So what you get is x dot 0 is equal to 0. Now let's look at the theorem number 3. What does the theorem number 3 say? So theorem number 3 is a very simplest one. So the theorem number 3 says, if you take the inversion of inversion, then it will be the same element. So how do we prove that? Okay. By the way, how did you get the inversion? Inversion is obtained using the identity element. That is, the you take the complement of a element. You take the element and its complement, you get the identity element. Element and its complement, you get the identity element. Now, coming to the x bar over here. So let's start with the x bar. So if you know very well, x bar is if you look at the theorem over here, okay, so x dot x bar is equal to 0, x plus x bar is equal to 1. Now we know that, okay, The complement of x is x bar. How did we get that thing, complement of x? Because we know that if you add complement, you get the identity element, or if you multiply the complement, you get the identity element for dot. So in this case, you say that complement of x is x bar. Okay, so instead of this x bar, we say that now look at this thing over here. So complement of x is x bar. So you go from this side. Let me change the color. Complement of x is x bar. What is the complement of x bar? Complement of x bar is x. You look at here. Complement of x is x bar. That is why when you add x plus x bar, x plus its complement, you are going to get 1. If you take this as x bar's complement is x. That is why you are going to get the identity. Look at here. X complement is x bar. That is why you get the multiplication identity. What is x bar's complement? X bar's complement must be equal to x. That is why you get the identity. So you look at here. The x complement is x bar. Now what is the complement of, that is x bar? What is the complement of x bar? So you come the other way around. What is the complement of x bar? Complement of the x bar must be equal to x itself, and that is the proof of the theorem. Now let's look at the theorem number 6. How do we prove that? X plus xy is equal to x. So how to prove that? So x plus xy, now what we are going to do is, we know very well, if you multiply it with 1, it's not going to change. How did you know that? You know very well, x dot 1 is equal to x itself. Okay, so you get it. Now we have this x dot 1, x dot y. So you take this as x, you take this as y, you take this as z. So what is the common thing? You take x dot y, so you take x common, and you take 1 and you take y. So from where did I get that thing? You know very well. So here we have x dot y, x dot z. So take x common and take y and z separately. So that's what we are going to do it. So you have this is x, this is y, and this is z, let's say. So take x common, take y here, and take z here. That is what is the postulate, and that is what you are doing. Instead of that, you took instead of y you have 1 here, and instead of z you have y here. They are all variable after all. Okay, now you get this one. Now you know the commutative law. You can say 1 plus y or y plus 1. So 1 plus y is same as y plus 1. How did this happen? Because you know very well, according to commutative, a plus b is equal to b plus a. This is commutative law. We know very well. So there is if you apply the commutative law, you get it. Okay, so you replace it the other way around. So there is no problem with it. It's a commutative. Now coming back to the thing, what is 1 plus y? We know very well. This is very too simplest one. So what is anything plus 1? Anything plus 1 is 1 itself. So this is what we are going to say. Anything plus 1 is 1 itself. Now what is 1 dot x? Again go back, and what is 1 dot x? We know that 1 dot x dot 1 or 1 dot x, the commutative it is x itself. So you go back, and what you see here, 1 dot x is x itself. So you started with the x plus y, and what you end up, x plus y is equal to x itself, and that's what is the proof. Now let's go to the next proof. X plus x plus y is equal to x itself. So you, in the previous one, what you have proved is x plus x dot y is equal to x itself. Now it is go to the dual out of it. So x plus y is equal to x itself. Now this can be, there is two ways in which you can prove it. One is using the algebraic equation. The next one is using the truth table. So let's try to prove it using the truth tables. Okay. So let's take two variables, x and y, and they are binary. So how many possible values you can get? 2 to the power 2. So two variables are there and they are binary. So 2 to the power 2, which is equal to 4. So what are the possible values? X is 0, y is 0, x is 0, y is 1, x is 1, y is 0, x and y are both 1. Now start multiplying x, y. What is xy? xy is 0 into 0, 0, 1 into 0, 0, 1, 0 into 1 is 1, I mean 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 1 dot 1 is 1. So you get that thing. Now you add x to it. 0 and 0 adding, you are adding it, so it is 0. 0 and 0 you are adding, it is 0. 1 and 0 it is 1. 1 and 1 it is 1. Now you need to compare these two things. Which are the one? The truth table of this whole equation must be equal to the truth table of this. So take these values over here, which is x here. Take this value, this is x dot y. You need to compare them. Corresponding value, are they same? So what you notice? So you notice that when x is 0, x plus y is also 0. When x is 1, the corresponding value of x plus plus 1 y is 1. So what does that mean? It means when x takes 0, the other equation also takes 0. When x takes 1, the other equation also takes 1. That means they are same. Let's try to prove the De Morgan's theorem. So again we are going to prove it using the truth table. So let's try to take two variables x and y, and they are binary numbers. So 2 to the power 2, what are the possible numbers you can have is 4 values you are going to get. What are those 4 values? When x is 0, y is 0, x 0, y 1, x 1, y 0, both are 1. Start taking x plus y. So what is x plus y? X plus y is 0 plus 0 is 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. Okay. Now take the complement of this one. So what is the complement of this? If x plus y is 0, complement of it is 1. If x plus y is 1, then the complement is 0. Now take the complement of x itself. So when x is 0, y must be 1. When x is 1, y must be 0. I mean sorry, not the y, sorry, the x bar must be 0. Now take the complement of y bar. When y is 0, the y bar must be 1, and when y is 1, the y bar must be 0, and that is true for the remaining two. Remaining, I don't have to say that. Now multiply them together. X bar dot y bar. 1 dot 1 is 1, 1 0 0, 0 1 0, 0 0 0. You're multiplying it. Now you need to prove that this part is equal to this part. So take the truth table of these two. So take the truth table of these two values over here, these two values over here, and see whether the correspondingly they are same. When x plus y bar is equal to 1, x bar y bar is 1. When x plus y bar is 0, the corresponding value of x bar y bar is 0. So that means the truth table of both of them match. That means to say that the two theorems are same. Two expressions are same. Now, whenever we try to prove the solve the Boolean algebra problem, we know in mathematics we have BODMAS. So we need to apply the operators according to their precedence. So precedence is a priority. So if you get not and or together in an equation, which part has to be solved? And that gives the priority. Now, according to the Boolean algebra, the priority is if you have anything inside the parenthesis, that has to be solved first. Then the precedence is for the not, and then the and, the finally it is or. So this is how you need to prove. This is how you need to solve the Boolean expression. That's all in this class. Thank you for your interest. We will meet again in the next class.